From the Library of Congress in Washington, D.C.
Good morning, and welcome to our 7th of 8 talks in our NASA lecture series this year. I am Stephanie Marcus from the Science, Technology, and Business Division. And today I think we can say, Houston, we don't have a problem because Houston is the world champions in baseball. Hooray! And I did see someone from NASA, from the Johnson Space Center, who was in an orange spacesuit and had all kinds of things hung on him. Go Astros. So, exoplanets. Everyone seems to love them. It's not enough to love our own planet. We have to love that which we know very little about. And today we have the perfect person to tell us about exoplanets. Our speaker is Dr. Padi Boyd, and she's chief of the Exoplanets and Stellar Astrophysics Laboratory at NASA Goddard. She has her BS in astronomy from Villanova, and she was originally more of a music, artsy kind of person, and then she turned towards astronomy later in high school, and look at her now. And then she went to Drexel and got an MS and a PhD in physics and atmospheric science. She's been involved with exoplanets going way back because she has worked with the Kepler Mission and the Hubble Space Telescope. And now she is also the director of the Guest Investigator Program for the Transiting Exoplanet Survey Satellite mission, which we like to call TESS. And we did have a speaker in 2015, almost 2 years ago in October, Stephen Reinhardt, who talked about TESS. And at that time it was supposed to launch in 2017, but Dr. Boyd says now March 2018 is the expected launch date. We do have a webcast of the TESS program if you don't learn enough about exoplanets today, but I'm sure you will. So please join me in welcoming Dr. Padi Boyd.
Well, thank you very much, Stephanie. Can you all hear me okay? All right, it was a real pleasure to be here at the Library of Congress. I am really excited to visit the building and the people and to talk to you about the very exciting field of extrasolar planets, excuse me, or exoplanets as we call them, planets around other stars. So I thought I would start off with a very thought-provoking engraving that most people have seen in some time or another in their lives. It's from the late 1880s. And it was an engraving that first appeared in a textbook about meteorology, the study of the atmosphere. But it's so thought-provoking, and it really has so many things going on in it that many people can read a lot into this engraving. It's someone who's peering beyond what is known around them, in the world around them, the sun, the moon, the stars. And they're peeking through, and they're catching a glimpse of what's going on beyond. And this particular image, you can see the familiar trees on the earth, the sun setting, moon and stars in the sky. And then beyond that, a picture of a mechanistic solar system. So some people associate this image with the birth of the scientific revolution, because human beings, ever since we've been able to sit around a campfire and talk to each other and share ideas, we've known that some stars are the same in relation to each other every night, and that others were wanderers. The wanderers were the planets, been known about for centuries, but it was only during the scientific revolution where scientists like Kepler and Galileo put the picture together, and Isaac Newton, of what was really going on in our solar system. So that's a moment that shows you a kind of transformation, someone seeing the world in a new way for the first time. And this has happened so many times in science, and I think it's happening right now in astrophysics as we're exploring the planets close to Earth now. Oops. I don't know what that musical signal was, but we're still seeing. I think this was a very transformational moment for many of us, too. Many of us who are old enough to remember this picture, which is called Earthrise. I'm just barely old enough to remember when it first appeared. and it made an impact to everyone on planet Earth. It was really the first time that the human race could think about what the planet Earth looks like from a distance. These were the Apollo astronauts, and as they were orbiting the moon, one of them turned around and took that beautiful shot of the Earth. The sun is illuminating both the moon and the Earth, and you get that sense of a pale, small blue dot that's floating alone in a dark, dark universe. It really gave us a sense of our perspective of the solar system. But up until even at that time, the solar system was the only set of planets that we knew for a fact existed. We'd known about them for thousands of years. We'd put them together in a picture of how the solar system works over the last several hundred years. So we know that the planets in our solar system orbit the sun, which is a typical star compared to the other stars in the sky. And the planets are on orbits that are defined by their distance from the star. The closer they are, the faster they go. And we knew a lot about our solar system. We could study it. We sent probes to it in the 60s and 70s and beyond. We learned a lot about the planets that orbited our star. But for so long, it was the only solar system that we really knew anything about. And I've picked this picture from an Isaac Asimov book because Isaac Asimov was so amazingly talented at marrying the science and his science fiction ideas. So he really brought science to humanity through his science fiction stories, and he also embedded them with great science. Of course, science fiction knew of many planets beyond our solar system. There are so many examples of stories that are so important to all of us that really depend on this idea that planets like Earth are plentiful throughout the galaxy and even in galaxies far, far away. So there are many scientists who are interested in exoplanets who can tie their first moment of really thinking about planets beyond our solar system to some moments in Star Trek or Star Wars, or something where they were exploring planets beyond our solar system. But for so long, those were just dreams and stories. And when we'd look up at the night sky, this is a picture actually from Joshua Tree of a beautiful dark sky, and you can see the band of the Milky Way there. The sun is one of hundreds of billions of stars in the Milky Way galaxy. And some lucky nights we're lucky to really look at a huge swath of stars. And for generations, all we could do was look at those stars and wonder, is the sun unique? Are we the only star out there out of hundreds of billions that have planets around them? And that was the only thing we knew for sure. But scientists are persistent. Our technology develops and allows us to learn more and more as time goes on. So one of the reasons we didn't know about stars that had other planets was because they're very, very hard to detect. The star's light vastly outshines a planet's light. Planets are just little specks compared to giant stars, 10 billion times brighter typically. But our technology got better and better so that instead of seeing the planets, we could allow ourselves to detect them indirectly. One method is called the radial velocity method. And what this relies on are just simple Newtonian mechanics. Remember, Isaac Newton put together a picture of how the solar system works, and it's based on gravity. And we know that all stars are obeying these laws. So if a star has a planet orbiting it, we know from Newton that they're orbiting a common center of mass. It's not the star being completely static and the planets orbiting around the star. They're actually both in orbit. The planet's orbit is bigger because the center of mass, where most of the mass is inside the star typically for a small planet. But that doesn't mean the star doesn't move at all. If our technology gets good enough, we can detect that tiny wobble from a star that's telling us that a planet is imparting that wobble on it. It's called the radial velocity method, and it was really getting going in the mid-90s. Of course, we were looking for solar systems that looked a lot like ours. We knew big planets were going to be the ones that imparted that signal strongest on the stars. But the big planets in our solar system are Jupiter, Saturn. They are way, way far beyond where the Earth is. They take years to go around the sun, 5, 10, maybe even longer years. So people were looking for signals in their data from big planets that they thought would be like Jupiter and Saturn. They were so focused on what they were expecting to see from our solar system that many of the scientists who were working this area missed the first signals. This is actually the discovery image. It's actually the confirmation image by a group, Jeff Marcy and Paul Butler. who confirmed a planet called 51 Peg b orbiting the star 51 in the constellation Pegasus. So what you see there is going up and down is the velocity of the star coming towards us and moving away from us, towards and away, in a perfectly periodic way that's telling us what the orbit of that planet was. It was actually on a few days orbit, less than 5 days, much, much closer than any planet in our solar system, and quite massive, almost the mass of Jupiter, to be able to impart that signal. This was a watershed event. It was like the Earthrise image for scientists, because we now had evidence that there were planets around other stars. And that first planet was so surprising compared to what our solar system has that we had to rethink how we were looking for exoplanets. So it's hard to read this in the light, but this is our artist's impression of what 51 Peg b looks like. Its orbital period is about 4 or so days. It has a very hot temperature because it's so close to the sun, 1800 degrees Fahrenheit. That's really hot. You don't want to live there. We don't think it's a habitable planet. And then as we start thinking about what that means to be habitable, we start to get a sense that the planet like Earth, maybe Venus, maybe Mars, are in a region near our star called the Goldilocks zone, where they're not too hot for water to exist on the surface, and they're not too cold for all the water to be frozen. So we started to find planets, but they were not in the habitable zone. And exoplanet discovery started to take off. There are several different methods you can use to discover exoplanets. And so in 2009, NASA finally completed a mission called Kepler. Kepler was actually dreamed of decades before it was built and launched by a principal investigator named Bill Barucki. He knew theoretically, he wrote a paper that said if you were very careful with your photometry, how you measure your light, that you could detect a tiny dip in the light as a planet passed in front of the star. That's called a transit. So finally, Kepler was launched in 2009 by NASA with one goal and one goal alone: to answer the question, how common is a planet like the Earth, so a small rocky planet like we live on, how common are those planets around stars like the sun at a distance that's in the Goldilocks zone? In other words, how common are we? Here's a transit. Many of you may have actually seen this transit. It's the transit of Venus. Do you see it? Anyone? It was visible in the morning sky. I think that was the one that was in the morning. You could get up on your roof with the right equipment and watch the transit of Venus. They happen very, very rarely, but they happen in pairs a few years apart. Venus is about the size of the Earth, and that's going right across our sun. So you can see all kinds of things in that movie. Let me see if I can start it over. So you see that the sun actually looks darker on the edges. It gets brighter as we go in. You can start to see some granulation on the surface of the sun. Stars are actually pretty active. They're not super quiet. Our star is actually very quiet as stars go. And you can start to see that haze around Venus, the atmosphere. Venus has a very thick atmosphere. Some of the sun's rays are getting, they're not passing through the atmosphere. It's actually dim around there. And then as it comes off, you can get a sense of the size of Venus. It's covering just a little piece of the sun, so its light is going to dim just a bit. Here's an example of what Jupiter would look like if it passed in front of the sun. It would cover up about 1/100th of the size of the sun. And you'd see a dip that you could measure, and you could get a sense of that size if you knew the star size very well. Here's what the Earth would look like. That's hard. So maybe you can't even see it, but it's there on the right side. And if this were a bit more high definition or darker, you'd be able to see some features on the sun, sunspots that are the same size or even bigger than the planet. So it's a real challenge to try to disentangle the signal from the stars from the signal of the transit. But Kepler was meant to do this. How did it do it? Well, we launched Kepler into a really interesting orbit called an Earth-trailing heliocentric orbit. So it's almost on the same orbit as the Earth, but it was a little bit further out, so it lags behind us. And that orbit was a very good orbit for us to stare without blinking at this patch right above the Milky Way galaxy. It's near the Cygnus and Lyra region of our Milky Way. If you're familiar with the constellations, you'll know to look out in the summertime near the summer triangle. And if you were to stare there without blinking for 4.5 years, you would be doing what Kepler was doing. Why is it so important that it stared without blinking? Well, a transit like I showed you of Venus, I said only occurs from where we can see every 200 years or so, and it only lasts a very short while. Well, the same thing is true of a planet like the Earth. It's only going to transit its star once a year, once every 365 days. We have to be perfectly aligned in order that that planet passes in front of the star as we're viewing it from our vantage point in the Milky Way. It turns out that we expect only about 1 in 100 stars are going to be aligned with us so that we would see transits. So you have to look at a lot of them. So we had looked at 150,000 stars, getting a brightness reading every 30 minutes for 4.5 years, pausing only to turn around and dump the data back to Earth so that we could detect these tiny transits in 1% of those stars, if planets were plentiful. But of course, one of the questions Kepler wanted to answer was, how plentiful are they? What I told you is that 1 in 100 stars would be aligned so that we could see the planets. But if only 1 in 100 stars has a planetary system, well, then your statistics go way down. You have to look at a lot to get some meaningful number if planets are rare. So we didn't know before Kepler launched what the situation was. So here's a graph that gives you our picture of exoplanets before Kepler launched, on the eve of our launch. And there, up at the top, are the several methods that we can use to detect planets. There's the radial velocity method and the transit method that we've just talked about. You could also imagine, if you're close enough, you could see the planet if you had the right technology. There's a couple blue ones on there. Eclipse timing is something where if you have some very precise way of timing a system, like neutron stars that are like rock solid clocks, you could see difference in what the times that you expect versus the times that you measure, and you can infer that a planet is there from that. No Kepler points on this yet because Kepler didn't launch yet. So what we see there are a bunch of massive planets, planets bigger than Neptune and Jupiter up near the top. And we see a whole bunch of planets that are on very short orbits. So at the bottom, we're looking at how long is the orbit in days. You see that big chunk of pink ones from the transit method. They're all like on a week's or shorter orbit. So we see a lot of massive planets. We see a lot of planets that are very close to their star. None of those are planets like the Earth orbiting in the Goldilocks zone. So let me show you what the first few years of Kepler taught us. There's another transformative moment in our understanding of what planets are like in our galaxy. So remember, that's just a little patch of our galaxy. It's actually 10 degrees by 10 degrees. So it's a fairly large patch of the sky compared to something that Hubble can see. But you can see what's happening is that we're going down to much smaller sizes. And in fact, if you look at where most of those yellow dots are collecting, they're collecting near the small planets. We're not picking up those big Jupiters. They're the easy ones to find. That's why we found them when we first started looking, because you can't miss them. They're in plain sight. And you can also see that we're pushing out a little bit towards longer periods. And there's, of course, still some Jupiters up there and still some hot Jupiters. Let me show you the newest catalog of Kepler planets. You may have seen a press release related to this within the last few months. The Kepler team, the Kepler mission is done now. It's on a new mission called K2, and what the team is doing is they're compiling all their statistics and really improving their pipeline software that finds the planets to give us a sense of what Kepler found. So the little yellow ones are the newest planets, and you can see that the improved processing is really, really pushing us down towards those smaller planets and towards longer orbits. You see where the Earth is there. We're really starting to fill in that region of planets that are on Earth-like orbits. We're still only talking about a couple of dozen planets. But remember, Kepler looked for 4 or so years. You've got to see several transits before you know you have a planet. So really, finding something at around an Earth or a Mars orbital period is at the limits of what Kepler can do. We found that planets were everywhere. This is an image that shows you that region of the sky, but now plotting some of those planets down on it as a function of how big the planets were. So there's big planets and small planets that are everywhere in the region that we looked. There's no preferential treatment. There's no stars that have them and don't have them. Well, one of the really key points that we found when we found so many transiting planetary star systems was that planets are everywhere. You can take what Kepler found and you can extract that to determine that pretty much every star out there should have a planetary system, and that 1 in 5 probably has a planet about the size of the Earth in an orbit where you could have liquid water, a habitable zone planet. 1 in 5. So when you look up at the sky next time, count 10 stars. 2 of them probably have an Earth-like planet in orbit. Well, Earth-like is a tricky thing to say. I'll say Earth size instead. Here's the distribution of planets, of the planetary candidates as of a couple years ago. So here's some surprises. So you see Jupiter-sized planets and larger are actually fairly rare in the Kepler Hall. And we've got a couple in our solar system, but most solar systems that we interrogated with Kepler really didn't have a huge planet like that. Also, we see a bunch of Earth-sized planets and a huge number of things that are bigger than Earth, but not too much. 1.5 to 2 times the size of the Earth. We call those super-Earths. And then you see this big, big peak at around Neptune or so. They're actually a little bit smaller than Neptune, up to Neptune size, and we call those sub-Neptunes. And as the data got better, this is actually from that recent catalog that I was talking about before. You could get much better statistical insight into the sizes of the planets. We actually see something we call the Fulton Gap. What it tells us is those small planets that are so numerous, they appear to come in 2 separate categories, 2 separate populations. One that we think are probably very similar to the Earth, like Kepler 452b. And by similar, I mean a small rocky planet with just a little bit of atmosphere, because believe it or not, the Earth has kind of a tenuous atmosphere. And then we think the other population are planets that are probably right around the same size in their core, but for some reason they have attracted and retained a huge atmosphere, bigger than Venus, maybe close to Neptune, the atmosphere being so big that you can't really have life there. It would be way too dense. 2 populations of small planets and a gap in the middle that may be telling us about 2 different formation mechanisms for the same kind of planets or the similar sized planets. But what's really surprising about this type of result to me is that we were learning so much about planets before by studying our own solar system. And now what we're finding out from Kepler is that the 2 most common types of planets out there, super Earths and mini Neptunes, we don't have one in our solar system. That's interesting. Were they here? Did they go somewhere? Did our solar system form in a different way? Or is it just small number statistics? We know a lot about one. This is a really thought-provoking animation that I love to show. It's called the Kepler Digital Orrery. When scientists first figured out the solar system, they loved to build things called orreries where you could turn a crank. You could see it on Asimov's cover there. And the planets would start to go around because they're like little mechanical systems. This is basically that idea applied to the Kepler multiplanetary systems. Because something else we didn't know for sure until Kepler launched is whether solar systems of planets with more than one planet, were common or rare. Now what we're finding from Kepler is that they are incredibly common. It's very common to find systems of planets. And when you find systems of planets around a single star, it's much more powerful because each one of those planets can tell you something about the same star. And since the planets interact with each other gravitationally, they can even tell you about the masses of the planets themselves. So you may have seen as it zoomed out and zoomed back in that you started to see our solar system on the same scale. So again, just another graphical reminder that Kepler was really studying those tight solar systems where the planets are going around weeks, months, out to a year or so. Whereas our solar system, we know of things on very, very long orbits. So you may have also noticed that there was a difference in the star type. The star type and the planet temperature were up there. Well, that's because Kepler was looking in one region of space at about 150,000 pre-selected stars. We selected most of them to be very similar to the sun, but it turns out that there are just a whole bunch of stars that are much, much smaller than the sun. There's a distribution of stellar sizes. And the sun, while it's a normal star in some ways, the most typical star in the Milky Way is actually a very low mass star, what we call an M star. It's just a way of categorizing stars. Some of them are only 10% the mass of the sun. But what that means is that if an Earth-sized planet is transiting a much smaller, much dimmer star, then the transit signal is a lot deeper. So you see on the right a transit signal around Kepler 186, which was one of the first Earth-sized planets in a habitable zone announced by Kepler. Compared to what the Earth transiting the sun looks like, much, much easier to find those Earth-sized planets around the smaller stars. Here's a gallery of some of the small, hopefully Earth-like, but certainly close to Earth-sized planets that Kepler has found, showing you their size by how big the circle is. There's Earth up there, sort of towards the top and the middle, and giving you a sense of the habitable zone. We're sort of right smack in the middle of the habitable zone, we think. We could exist closer in. We'd have a completely different climate. We'd probably be a different species. We could also be pushed out. We would have different characteristics as well, but we believe liquid water could have formed and existed on the surface and life could have flourished. And we can set that Goldilocks zone or habitable zone by how much radiation planets are receiving from their stars. So on the top axis there, you're getting a sense of what type of star are these planets around and how much sunlight they're getting from their star. How is that habitable zone defined? So you see we've got a lot of smaller planets around the smaller stars for the reasons we talked about before. And even in the Earth region, there are a number of planets there. So they're still very hard to detect, but we are finding them. Dozens of habitable zone planets found by Kepler. This is again an update from that latest catalog. The yellow ones are the new ones. So you can see that last run of the Kepler data found habitable zone planets and small planets that were getting closer to Earth analogs, which is exactly what we were expecting would happen with Kepler. That as the data came down and we got more data and we refined our methods, that we would be able to really push down into a habitable zone around a star like the Sun. So I mentioned that the M stars are abundant in our galaxy. 7 out of 10 stars in the Milky Way are thought to be small M stars, and the stars closest to us are small stars. So they're important. They're becoming increasingly important as we think about finding planets, because what Kepler told us is that planets are everywhere, and we saw that a lot of M stars seemed to have a lot of smaller planets around them. That it's common to make smaller planets around smaller stars. The other thing that's really exciting about them is that the habitable zone is really crunched in near these small stars, and that means that that transit that you're looking for, or anything you're looking for on that periodic signal, happens much more often, weeks typically. So if you want to observe something over and over again for a planet, a small planet around an M star is going to give you a lot more opportunities in a given, say, observing season at a telescope than something like the Earth around the Sun. So a lot of our attention is being turned towards the smaller M stars in the galaxy now when we think about how we're going to take the next steps from Kepler and find those really Earth-like planets. But there are some problems and some challenges with M stars. It turns out that M stars are incredibly active. So sometimes you're probably hearing about solar flares that they're predicting are going to perhaps impact your cable signal or maybe the GPS for a little while, or maybe you're going to be able to see an aurora down here in southern latitudes because of the sun's activity. Remember, I told you the sun is a very calm, low activity star. M stars are hundreds of times more active. They give out huge flares that dwarf solar flares, and they do it much more typically. So much more often. That means any planet that's really close to that M star and going around really quickly could be bombarded, probably is bombarded with high energy radiation all the time. So even if they're in that habitable zone, it could be a trick for it to really be something where you would get habitability happening. Also, planets that are close to stars tend to synchronize their orbit and their spin, just like the moon has synchronized its orbit and spin with respect to the Earth. So we always see the same face of the moon facing the Earth. A planet would always see the same part of the sun. Or I should say it the other way around. If you're on a planet that's in one of these M-star orbits, you're quite likely to have gotten tidally locked, and you could either be on the side of that planet that always faces the sun, or maybe on the side that never faces the sun, or maybe lucky enough to be on that terminator area. Maybe the planet would wobble a little and you'd get something like a day-night cycle. But typically, we expect these to be tidally locked, which gives you all kinds of different habitability issues. But we're still working hard to study these phenomena and figure out what could really be going on in these systems that are so different from ours. And one thing that I think is really exciting about this particular area of research is it really joins together all the areas of astrophysics. So you have to understand our sun very well, the flare dynamics and time variability, to have some sense of other stars that are like it, and to be able to compare what's happening on other stars as far as their flares go with what we know so well about the sun. Sun's very well studied. We have reams of data about the sun. Also, we're learning about what happens to these planets around other stars by studying the planets in our own system, getting better refinements of how our own solar system formed. Why is there water in some places and not others? Was there water that escaped, for example, in Mars? And we have a lot of information about the atmospheres on the other planets in our solar system because we've sent probes, and we keep sending probes, and the probes get better and better all the time. So we're able to take the Earth scientists' ability to model the Earth's atmosphere and apply it to planetary atmospheric modeling, and then tying that with the sun's variability, getting a picture or a model of what the exoplanet atmospheres could really be like. So it's just a very exciting time to be in any area of astrophysics, because anything that you do has some tie-in to understanding the atmospheres around these planets. So we know the planets are there, and our next step is, how are we going to find out about the atmospheres of these planets? What's in the atmosphere? How big is the atmosphere? Do they even have an atmosphere? I'm going to take a little bit of a detour now to a system that got a lot of attention earlier this year, and this is called the Trappist System. Has anybody heard of the Trappist System before? Yay. It was very exciting. It was one of NASA's biggest days as far as like communicating a message goes. A lot of people heard about the Trappist result and downloaded the images and watched the press conference and read articles online. What's Trappist? Trappist is a really small star, like we were talking about, that was discovered with a ground-based telescope to transit. And the team that discovered it convinced the Spitzer Space Telescope to stare at it for a very, very long time. This is 500 hours of Spitzer data, again, uninterrupted, because they knew that there were a couple of systems that were transiting, and if they looked for a long time, maybe they'd find more. So this is the discovery image of many of the planets in the Trappist system. There's actually 7 Earth-sized planets, Earth-size-ish planets in this system. They're small planets around a small star, and they're about 40 light years away. It's actually really close in the Milky Way. It would take us about 800,000 years to get there if we were going at the New Horizons speed, the fastest thing we've ever sent away from Earth, but still close. Relatively speaking, it's close. Some people actually think that the Trappist system is more analogous to Jupiter and its moons. Jupiter has moons that are about the size of the Earth too. And Trappist is a really small star. You could fit the Trappist system well within our solar system. Those planets orbit Trappist on orbits of days, weeks, and months. So they're transiting all the time. Sometimes you can see 2 of them transiting at the same time, and if they're really a lot alike, you can boost the signal of what you're detecting by looking at the 2 planets passing in front of the sun instead of 1. So there's a lot of interest in Trappist. We know that they're small. We saw them interacting with each other gravitationally, so we can measure their masses. They're so close that it's a fairly bright target, even though it's a dim star. Absolutely, it's still close enough that we can observe it very well. So it's going to be observed for decades. It's going to be a touchstone system in our exoplanet studies. This is just another example of the Trappist planets on top compared to some of the smaller bodies in our solar system, the terrestrial bodies. And you can see where it says planet radius there, the third down, that they're all pretty darn close to 1 Earth radius. So they're a really good size. And some of them are in the habitable zone. They should have formed in a place around that star where they had ice and water, and as they migrated in, kept some of that water on their surface. So they're also excellent candidates for looking for life signs or at least water signs. How are we going to do this, and how are we going to find more systems like Trappist? Well, we're going to launch something called TESS. Transiting Exoplanet Survey Satellite, as Stephanie mentioned earlier. It's actually a fairly small telescope. It's 4 cameras that are pointed in a row, and it's going to launch in 2018 March, and it has one purpose. It's going to do an all-sky survey of the stars near us to look for planets transiting nearby bright stars. So Kepler wanted a statistical answer, and it looked at stars that were very far away. TESS is going to look for those transiting planets now around our nearest neighbors. We know they're out there. We're going to find them. Here's an overview of the mission. It's what we call a NASA Explorer mission. NASA has big missions like Hubble and medium missions like Explorers. We launch balloons and sounding rockets as well. It's managed at Goddard. The lead institution and science team is led by George Ricker at MIT. It's being built down in Virginia at Orbital now. I have a beautiful picture of it all coming together. It's going to take 2 years to survey the sky. It's going to do the southern hemisphere first for 1 year, and it's going to turn over and do the northern hemisphere. And they've designed it so that they can detect enough exoplanets this way that they can then go to the ground-based follow-up observatories to confirm them and measure their masses. 50 small planets at the end of this. These cameras are really wide field compared even to Kepler. So one camera you could actually put the entire Orion constellation into. Go out some night when it's clear and look at Orion. It's a huge constellation. That's one of 4 cameras. So it's really looking at a huge swath of the nearby stellar neighborhood. Here's a comparison of the Kepler search space. So Kepler was looking at one region, at basically a cone, where the average distance of the stars was 3,000 light years. And it only looked at less than 1% of the sky. That is TESS's search space. We're going to look at virtually the entire sky. There are definitely some gaps, but those stars are more like 200 light years near us. Lots closer. They're going to be brighter. And they're going to be all over the sky. There it is. It's taken a long time to take a picture like this of TESS, but that's a solar array test. The spacecraft is all put together. That's the antenna you're seeing looking at you. That's going to beam our data down every 13.7 days once we go around that orbit. You can't really see the cameras, but they're on top. So we're really excited for TESS. We know it's going to find transiting planets. We can't wait to get to the telescopes and find out what their masses are and maybe have another few Trappist-like systems where we can really start to figure out what's going on in the atmospheres. But all of these missions I've been talking about so far, really what they're doing is they're discovering exoplanets. They're collecting where the exoplanets are. And we're learning about the sizes of the exoplanets, that there's a wide variety of sizes. But we don't know very much more. There's more than 4,000 exoplanets known right now, more than 4,000 just from Kepler alone as candidates. We're not sure what any of them really look like the way that our own solar system planets are known. So how are we going to get there? Well, we have to turn to the most powerful telescopes that exist today and that we're launching soon and that we're planning for the future in order to really get these answers. We've got enough data now that we can really design these experiments well to take these next steps. So I'm going to take a few minutes, just talk about what direction, one of the directions that we're going in. This is an artist's concept of some work that's being done with the Hubble Space Telescope right now. It's been going on for the last few years, and there are several large programs that are devoting Hubble Space Telescope time to measuring the spectra of what we call those hot Jupiters, those very massive planets, to look for spectral signatures, little parts of the light that are missing where elements have been absorbed by the light. So what we see here is a signature of methane in a planet's atmosphere. Methane is one of the gases that we think could be a biosignature. A lot of biological material makes methane. It's not easy to keep methane in an atmosphere if there's no source for it in certain conditions. So methane is exciting. We can actually see it in a Hubble spectrum. These are just really the baby steps that we're taking here. That doesn't tell you where the methane came from. It doesn't tell you a lot about the atmosphere other than that you've seen a methane line in absorption. But we do know that the James Webb Space Telescope is going to be able to take the next step. So James Webb Space Telescope is launching in 2019. You can see it's quite a bit bigger than the Hubble Space Telescope. Hubble Space Telescope mirrors 2.4 mirrors. JWST dwarfs it. It's hexagonal mirrors that come together and can reposition themselves. It has a sun shield there at the bottom that's the size of a tennis court that's going to keep it very cold because it's going to make measurements in the infrared, so red part beyond the red part of the visible spectrum. That's where a lot of exciting stuff happens in astrophysics, both for exoplanets and for the distant universe. That's actually a picture of the James Webb Space Telescope. It was put together at Goddard in the clean room, and that was one of the days that it was facing the window. So it really is huge. It really is ready to roll. They're down testing it in Johnson. It's actually out of testing now. They're warming it up in the big chamber where they did a lot of the Apollo testing. Next, it'll go off to get the sun shield mated to it, and it'll launch from French Guiana in 2019. We're so excited about what it's going to find. There's also been a lot of interesting work done in our own solar system studying the Earth. There are a lot of planetary missions that you could turn around and have them look at the Earth. The picture on the left is actually an image that was taken, I believe, from Cassini. You see that little blue dot in there is the Earth from the distance of Saturn. And that's better than we're going to see exoplanets around other stars, but it's still so tiny. But there were efforts made to tease out the spectrum of the Earth, both in the light that's coming right towards you and also as a transmission spectrum. So when we're looking at a lunar eclipse, where the sun is behind the Earth and we're looking at the moon that's red because the Earth is blocking the light on the moon, but some of the light is passing through the atmosphere and bouncing off the moon. So you can get some spectral signatures of the Earth in these ways that are not directly looking at the Earth. And we know that we can see some signs in those Earth spectra that tell us that biosignatures are on the Earth. So that's a really exciting prospect for the future. If we can do the same kind of thing with nearby exoplanets, can we see evidence of water, evidence of clouds, evidence of tectonic activity? We also know that it's possible, if you were to, say, be looking at the solar system and you had a really good telescope in your alien universe or galaxy, if you could see the Earth and Mars and Venus, we know that you could tell those spectra apart. They're all small planets, they're all close to the habitable zone, but they have specific features in their atmosphere that differentiate them. And particularly as you go out towards the right of that curve, that's a spectrum and it's going into the infrared. We can see that the carbon dioxide feature is so strong in the Earth compared to Mars. Other features in Venus, all that carbon dioxide in the Venus atmosphere causing those deep lines. So this is, again, exciting evidence that we may be able to disentangle features of planets that tell us if they're Earth-like or maybe more like Venus. And there's some really exciting work going on now as we plan the telescope that is going to be the next generation JWST. So while we're excited about launching this huge JWST telescope in 2 years, we're also thinking about what have we learned from building JWST that will let us take the next step. Let us build an even larger mirror. Let us take even more sensitive measurements. This is a really exciting simulation that has just come out recently by a group at Goddard led by Aki Roberge. She's a scientist that's working on a mission concept called LeVoir, the Large Ultraviolet Optical Infrared Telescope. And one of the things they need to know to build LeVoir correctly is what could you expect to see if you were looking at the solar system from about 12 parsecs away? Could you even be able to disentangle all that stuff around the sun? We know there's a lot of dust in the solar system. We know that when you're looking at a star, there's all kinds of stuff in the background stars, even background galaxies. This group has put together an extremely sophisticated simulation to help us understand what we would see if we could look at the Earth from a distance with something called a coronagraph. And the coronagraph is being designed, again, to be optimized for LeVoir. There's the Hubble mirror, there's the JWST mirror. Look at LeVoir. It's going to be yet again huge, but achievable now. We know we can do something like this. Let me show you a little movie of what a coronagraph does.
A distant star is orbited by two planets. One looks similar to the Earth, the other is a gas giant. When viewed from a distance, the two planets disappear into the glare of their sun. How could we ever find these planets all the way from the Earth? By using a space telescope with a coronagraph to separate starlight from planet light. As the star's light passes through the telescope's large mirrors, it picks up small distortions. Diffraction adds concentric rings to the image we see. To reveal the planets, first a coronagraph uses a mask to block much of the star's light and redirect the remaining light to the outer edges. A washer-shaped device can now block most of the rest of the star's light. Because the planet's light comes in at an angle, it misses the mask and passes through the center of the washer. But when we turn up the image signal by collecting more light, we can see that the planets are still hidden under blobs of leftover starlight. To remove these blobs, the coronagraph has a special deformable mirror that can change shape by using hundreds of tiny pistons. This can correct distortions in the light beam. As the mirror deforms, the blobs of light as seen in the monitor slowly begin disappearing, finally revealing the brighter of the two planets. Afterwards, the fainter planet also comes into view. We can now see objects more than 1 billion times fainter than the star. And if the light from these planets is passed through a prism, we can spread it out into rainbows of color. But some colors are missing. They were absorbed by gases in each planet's atmosphere, giving us important clues about their composition. The search for life in the universe has taken a new step forward.
So that's hopefully a pretty good explanation of what a coronagraph does. It's really exciting engineering and math and science and software, and we believe it is going to be able to cut down so much of the star's light that we would be able to differentiate Earth, Venus, and certainly Jupiter if we had a telescope like LeVoir at the right distance. So this is extremely exciting. It's definitely our next steps that we would like to take. LeVoir is just one of many large missions that NASA is studying. There's 4 large mission studies happening right now. There are 2 that are focused on exoplanets. LeVoir is one, and another one called HabX for habitable exoplanets. They share a lot of similar characteristics. They want to have a big mirror, want to have a coronagraph on board so that you can block out that starlight and start to see the planet's light and take spectra of it and find out what's in the atmosphere. But they just have slightly different mission characteristics. LeVoir is meant to do as much in the distant universe as it is to do in exoplanets, whereas HabX is a bit more focused in its science case, but it can also, of course, do lots of astrophysics as well. And we're waiting to see what the community directs NASA to do. Every 10 years, the country takes part in a decadal survey of astrophysics, and this directs the government science centers about what they should focus on in the next 10 years. So we're gearing up for the next decadal survey. It'll be happening in 2019 and 2020. Those 4 mission studies I was talking about, they will be going into the decadal survey. We're waiting to hear what the community of scientists that are involved in that recommend. We're certainly hoping LeVoir and HabX are very highly ranked so that we can start to really tease out these exoplanet atmospheric signatures. This is sort of just the sweep of NASA and ground-based astrophysics missions that are focused on exoplanets right now. I showed you some Hubble results, some Spitzer results. We talked about some ground-based results. We looked at a lot of Kepler data here. I told you how excited we are for TESS to find those nearby transiting exoplanets we know we're going to find and be able to follow up with Hubble and the James Webb Space Telescope. I didn't even get a chance to talk about the Wide Field Infrared Survey Telescope, and I can't because I don't have time, but it's going to launch as well. And then that last mission around the bottom there is this future mission that the decadal survey will tell us what it will be like. So I hope I have convinced you that we really are standing on the edge here of our knowledge of what we know about our solar system and extrasolar systems, and that we've started to peel back that veil and put together a much bigger picture of how planets exist around stars, and we'll take the next step to determine how they formed around stars and around our sun, and we're soon to take the next steps in determining what those atmospheres around those planets look like and whether or not they have elements in them that we could tie to biospheres, life, or compatible with life. So I hope that the next time you look up in the sky at the Milky Way, instead of seeing something that shows you that there are billions of stars in just our galaxy and so many galaxies out there, that you'll also think about the planets that are there that you can't see, the ones that we didn't know about when I was a kid and that we know now are everywhere, and think about what we're going to find out when your kids are my age. It's a great explosive time. So this is a picture of Galileo's telescope. It's a scale model. And it was brought up on the Hubble Space Telescope servicing mission, the last one by astronaut John Grunsfeld, who's also an astrophysicist. He's known as the Hubble repairman. He's the last person to touch the Hubble Space Telescope in orbit. So if you can squint your eyes, you can see both telescopes there, Galileos Telescope and the Hubble Space Telescope. 408 years between the two, and I think we're just at a very exciting time where knowledge is explosive in this area. So buckle up and please keep reading about it. Thank you.
Thank you so much. And if anyone has questions, we'll take them now and repeat them.
Okay. Well, let's start in the front and go around.
So, just maybe two questions if I can cheat. Can we not get a pretty good idea of the composition of particularly the smaller planets, or if that's what we're most interested in, perhaps? If we know their density, I mean, we know their mass, we know the size, can't we tell if there's perhaps water there from the density of the planet? And are we at a point sometime in the near future where we might be able to detect moons around these larger gas planets, that we've been finding?
So those are great questions. The first question is about whether the density gives you everything that you would need to know about the planet, and the second question is whether we could see exomoons, moons around exoplanets. So the first one, you're exactly right. You've hit the nail on the head, and that's why when I was talking about TESS, I focused on the fact that we are going to detect a lot of exoplanets, but that we're expecting that 50 of those will be able to follow up with ground-based measurements to measure the masses. So what Kepler and the transit method in general do just gives you the size of the planet, the radius. We don't know the mass until we've measured it through a different method, usually radial velocity. And the test targets are going to be so close and so bright that we're expecting several dozen will be amenable to really accurately measuring the mass. And so that if you know the star very well, the size of the star, then you know the size of the planet from the transit. And once you've got its mass, you've got its density. And that gives you a huge amount of information about the composition of the planet, its bulk composition. But there's a whole bunch of ways that you can make an average density out of, either a differentiated planet like the Earth, where we've got a lot of iron in the center, and then the crust is a different density and a slight atmosphere, or you can imagine putting that together in a slightly different way where you would still have the same common density. So it's a really important step, but it's not enough to tell you everything. Yes? Oh, there's a second question. Oh, exomoons, sorry. And yes, we do think that the Kepler telescope was precise enough that it could have measured exomoons. It's a little bit trickier to do that because it's not, so the pipeline for Kepler is just meant to find transiting planets. Finding transiting exomoons around a planet requires like another level of effort in the pipeline. There's a huge amount of data in the archive. I wouldn't be surprised if someone were to try to attack that problem in the next few years, but to the best of my knowledge, they have not announced any exomoons yet. They have announced some exo-Trojan asteroids. So we have the Trojan asteroids in our solar system that are in very special orbits compared to the planets. So they make a triangle, for example, with the Sun, Jupiter, and an equilateral triangle. There's two areas where asteroids can be stable and collect and coagulate. So if you scale a lot of the Kepler planetary systems onto the same scale, you can start to see signs that look very consistent with Trojan asteroids, which is exactly what you'd expect because gravity is the same everywhere. Yes?
Can you talk a little bit about the time factor? Kepler looks at one point and stays there for a long time and collects data, but doesn't make a decision on its own. The data comes back and decisions are made what the data is collected. Is there something that's coming in like a hound dog idea where you talked about you're pointing back at the Earth and collecting data, taking something that Goldilocks type of scenario would be for the Earth, and then speeding up the process of changing sectors and saying, all right, we're in this area, we've decided this is long enough to determine the transits, move to the next area and look for that type of Goldilocks perspective of an Earth, of whatever that is, from a perspective of oxygen or water or whatever consideration we're looking for that we would consider for life. Is there something like that? Versus you don't want to miss anything, but you're so much time is spending on the majority of things not being the right thing.
Right. So the question is to talk a little bit about how the time axis impacts your ability to detect planets. And Kepler pointing in one direction meant that while we were really interrogating one patch of the sky very intensely, we were missing almost all of the sky during that time. I think that's the point, right? And so for TESS, so no, nothing so sophisticated is in the near-term plans like that. But you can imagine putting together two simpler missions to get where you're going. So TESS's main difference from Kepler is that it stares in one region of the sky with those 4 cameras for 27 days only. And then it's going to rotate to like a next slice of the sky. The camera that's at the bottom or top is basically just rotating but looking at the same stars. So those stars will be monitored continuously for about a year, whereas the other parts of the sky, we're only going to have 27 days worth of data on those stars. So we're going to be, it's a preferentially red filter, so we're going to be preferentially finding transits around those dim, low-mass stars where you can see habitable zone planets in a short amount of time. But currently there's no effort to like dynamically change your time length based on what you've found so far. You can use the TESS results to then go to telescopes and do the more sophisticated stuff. Yes?
Yeah, when you find your biosignatures, being optimistic that you will, what degree of certainty will you have that you've found something that might signify life?
Oh, that's a really great question. And there's actually a lot of people that are working on that particular question. As I was talking about earlier, exoplanets has become extremely multidisciplinary. So, the astrophysicists are capable of developing these amazing telescopes with the ability, to really detect signatures in a spectra. But we also need atmospheric scientists to do modeling that tells us what are the possible sources of that feature in an atmosphere. What could be tricking us? What could look like a biosignature that isn't? And so we're using all kinds of information that we have from Earth science and from planetary science and just from modeling to start to answer those questions. So I think it's going to be very similar to the answer about like once you've got the mass, does that nail down everything that the planet is made of? We're going to have a similar answer for spectral lines and potential biosignatures. I think when we find something we'll know it is a potential biosignature, then we're going to have to do an awful lot of work, modeling, theory, and just measuring many other systems before we have a sense of how secure we are in that.
Just to follow up, and then what would be the next step once you've done some of that modeling? What would be the hope, like you said, when our kids at your age or future generations?
So I have a 7-year-old. And I am fairly confident that when he's my age, he's going to be able to go outside with his kids and point to a couple stars in the sky and say, that one right over there has a planet a lot like Earth. We know it's about the right size. We know that liquid water does exist there, and we think that there could be life because we know of these things. The next step is not up to my generation. Keep going this way and then come back. Yes.
I know there was an earlier mission proposed that hasn't been launched yet or planned, the Terrestrial Planet Finder.
Mm-hmm.
Is there an upcoming mission that's analogous to that, or how far off would a Terrestrial Planet Finder type mission be in the offing?
So some elements of the Terrestrial Planet Finder can be found in the LeVoir concept. But you can think of LeVoir as a re-engineered version of the Terrestrial Planet Finder. So the question was, how soon will something like the Terrestrial Planet Finder be realized? And so LeVoir takes some of the best ideas of the Terrestrial Planet Finder, and it takes all the information we have right now about the exoplanet populations we know of to design a mission that can really tell us something about what we know we're going to see. When the Terrestrial Planet Finder was first being designed, we didn't really know that much about the exoplanet population out there, and then some of the other things that might have made it very challenging to visually see planets, like how much dust was in the system. But we're taking what we're learning now about systems to make LeVoir even stronger and better. There's always a next step, though, and there's people that are thinking about what do we do even beyond LeVoir. And so there are some ideas about building super large mirrors in space using astronauts or robots near the space station, or you could launch pieces of it and put it together like a Lego. And then, of course, very much more sophisticated coronagraph technology. The movie that I showed you about where we're going in coronagraphs now, we've made huge strides there in the past decade, but we've got a long way to go there too, and you could see some kind of transformative technology there for direct imaging that you'd want to fold into the next mission as well. Yes?
Ages ago, I remember reading that we shouldn't get too excited about exoplanets because there are so many double stars out there, and double stars were less likely to have planets. I didn't hear you mention double stars at all.
You are right. I didn't have time to mention them at all. So you may remember that scene in Star Wars where Luke Skywalker goes back to his childhood home and he sees something terrible, and he goes out on a hill and he watches the sunset, and it's 2 stars that are setting, not 1. And people said at the time, George Lucas was, that was fantastical. You're not going to have any stable planets around binary star systems. There are actually planets around binary star systems when we found them with Kepler. The first circumbinary planets were found just a few years after the mission launched, and there's quite a collection of them. So that opens up a whole new set of questions about the stability of planetary systems. Where did they form? Do they form somewhere else and migrate in? Did they form around one star, or did the whole system form, as one? And have they interacted? Had they been around one star for a while and the other? It's fun. It's a lot of fun dynamics in that one. Yes?
Actually, yeah, my question was sort of based on that. How is binary or even tertiary, if that has ever been a situation, how has it affected the means for Kepler and maybe even future tests to elaborate on these exoplanet findings? Have they impeded it, or they, I guess, even more fascinating, for lack of better phrases?
So the question is, how does the binarity of many stars impact the results that we're talking about with Kepler and TESS? So we know that about half the stars in our galaxy are found in binaries and half are single. And lots of what I've talked about was sort of implicitly suggesting that these are single stars. And in fact, we know that about half of them aren't. So there's a great effort that goes into taking a Kepler planet candidate and turning it into a Kepler confirmed planet. And one of the things we have to watch out for the most is whether a binary star is tricking us. Because if you see a planet that's going around one star, you're gonna get a certain size estimate, but if it's actually 2 stars that are giving you the flux from the star, then the transit's going to look much smaller, and you're going to make the mistake that the planet is smaller than it really is. So there are efforts to go into like direct imaging of these systems to see if we can get very high resolution imaging and look for binary pairs. If they're very far away, that's also very challenging. So there are also some statistical arguments about whether this is a single star or a binary, and then also we can look at the data itself and see how the light moves on the detector to determine if there's something fooling us. Yes. Should I take one more question? It's 12:31. Okay.
Can you speak at all? It didn't mention if there was any significance to the location of where these missions were looking. Like Kepler seemed like it was kind of a somewhat arbitrary area, this spot and this distance away, and then the next mission is looking specifically only 200 light years away.
Mm-hmm.
They're both for Kepler, the location, but also the distance of the two of those. A reason why those matter?
Sure. So the question is, say something a little bit about basically the mission design. Why was Kepler chosen to look where it looked, and why is TESS looking at the 200 light year sphere around the Earth? So yes, there are good reasons. And there was a lot of debate and discussion and collaboration that went into deciding what the final Kepler field would be. We knew in order to do the mission that it had to be staring, so it had to be somewhere where it could look for 4 years straight. We wanted to have lots and lots of stars like the sun, so you needed a relatively dense patch of the sky, but you didn't want to be so close to the Milky Way that you had a lot of crowding, that your typical star would have other stars nearby that would dilute the signal. So you wanted to get far enough off the Milky Way plane that you'd have about 150,000 sun-like stars that you could put little postage stamp patches on top of to get the light curves. And another reason that position was chosen was because there were a lot of ground-based telescopes that could get on that part of the sky pretty quickly to confirm the planets. For TESS, once TESS was being finalized, we of course knew from Kepler that planets were everywhere, and so that made the choice of looking close, looking nearby, much, much better. We know they're going to be there. So now you can design TESS in a way that's a lot different than we design most astrophysics missions, where we're trying to look at really dim things. TESS is really meant to look at bright stars. Most telescopes saturate that when you look at bright stars, but TESS won't. So it was intentionally designed to be shallow, so that it's only going out to 200 light years, because we know there are more than enough stars in that area that it is sensitive to, that we expect thousands of planets and hundreds to be with measured masses.
Well, thank you very much.
Thank you. Thanks for all your good questions.
This has been a presentation of the Library of Congress. Visit us at loc.gov.